Good afternoon. Welcome to the Diesel Technology Forum's webinar, Reliably Saving Lives in Electricity, Diesel Generators. During the presentation, all participants will be in a listen-only mode. As a reminder, this event is being recorded. To ask a question at any time during the event, submit the question via the chat Q&A box. We encourage you to ask questions at any time during the presentation. Your questions will not be viewable by other attendees and will be addressed during the Q&A at the end of the session. I would now like to turn the call over to your moderator for today, the Diesel Technology Forum's Director of Policy, Dawn Fenton.
Thank you, Kristen, and thank you everybody for joining us for today's webinar. We have a great panel of speakers for you today. We'll be speaking about diesel power generation, where and how it is used, technology developments, and new market opportunities for using this equipment. This is actually the first of two webinars we'll be having this week. The second one will be on Thursday at the same time at 2 p.m. Eastern, and that one is titled Powering the Future, Trends Shaping the Use of Diesel Power Generation. If you are not already registered for that and you're interested in registering, you can go to the Diesel Technology Forum website at www.dieselforum.org/webinars, and you can register for that as well. It is also a free webinar. Well, I'm sure many of you are familiar with the Diesel Technology Forum because you've been on our past webinars. For those of you who are not, just a little background. The Diesel Technology Forum is a nonprofit educational trade association that works to increase awareness about clean diesel technology. Our membership includes companies across all segments of the diesel industry, and we undertake a variety of programs and activities to inform policymakers, the media, and equipment users about technology advances and the industry's contribution to a clean energy economy. In addition to hosting webinars such as this one, we conduct technology demonstrations and policy briefings and have a range of educational materials on our website. For those of you who are interested in learning more about the Diesel Technology Forum, I encourage you to visit that website, as I mentioned before, www.dieselforum.org. In terms of today's webinar, we will hear from each of our three speakers, or after we hear from each of the three speakers, you will have an opportunity to hear their answers to questions that you might have. I would invite you to submit written questions throughout the session during their presentations, after which, when the presentations are concluded, I will read as many of the questions as I can in the time remaining, and I'll read them out loud for the benefit of all participants and then direct them to one of our speakers for them to respond. I also want to remind everyone that today's webinar is being recorded, so you will have an opportunity to download presentations or even listen to the entire recorded session, including the Q&A portion, within a day or two after the event by visiting our website. Now, with that, I'd like to move ahead to our speakers, and as you can see, they're listed here on the slide. We have Mike Doffenbach, who is with MTU On-Site Energy. We have Chad Dozier, who is with Caterpillar, and Mark Foreman, who is with Enernoc. So let me first start by introducing Mike. Mike is he's been working in the engine generator power generation business since 1977 with Cato Light Corporation, and then subsequently with MTU On-Site Energy in Mankato, Minnesota. During his time there, he held various positions related to design and applications engineering, including being a project manager, working in industrial sales, and even training before returning again to industrial sales as a sales application engineer, where in the position he works in today. His background is in math and physics, and he's received his education from Mankato State University. So with that, Mike, I want to thank you very much for joining us today and invite you to share your presentation with us.
Thank you. Hello, everyone. Welcome to the Reliability Saving Lives and Electricity Diesel Engine webinar. Today our discussion will focus on diesel engine-driven generator sets. We limit the discussion to the high-speed diesel engines specifically designed for generator drive. These engines are similar and actually are derived from the same basic diesel engines used for automotive, heavy truck engines, heavy equipment engines, mining equipment, marine, and other equipment powered by diesel engines. The main difference a generator drive engine has from another diesel engine is the generator drive engine runs at a constant speed. The engine output torque varies as the electrical load varies. The speed must remain constant, so the generator output frequency is constant. In North America, the engines typically drive 4-pole generators at 1800 RPM to maintain the 60 Hz electric power frequency at the desired voltage. The generator drive diesel engines are a small percentage of the diesel engines manufactured each year. So what do the diesel engine generator sets do? Where are they used? Why do we have them? We all take our utility power for granted in North America. This power is generated by electric utilities using coal-fired power plants, nuclear power plants, hydroelectric power plants, and a number of alternative energy sources, such as wind power and solar panels. When this power is required to operate our lights, office equipment, electric power tools, motor-driven devices, electric heaters, and all the creature comfort devices we can find to plug into a receptacle, we expect it to be there. Most of the time, this is the case. There are occasions when utility power becomes unavailable. And when this happens, it can be a momentary inconvenience. It may last a few minutes or a few hours. In extreme cases, it can last for several days. These power outages may be caused by events beyond the control of the common user, such as power lines going down from natural causes, wind, storms, ice, snow, flooding, etc. Sometimes the lines are knocked down by a tree limbs, or an automobile crash. Sometimes the power failure is due to equipment failures, such as transformers overheating or shorting out, switches failing, power plant failures, or overload on the grid. Sometimes power outages are caused by people opening a circuit breaker unintentionally or in error. Using electric equipment improperly can cause a local failure in a building by causing a fault or opening a main circuit breaker. Whatever happens, the power is out. Depending on where you are at, this loss of power issue may be more serious. I'm showing a short list of applications where loss of utility power is considered a serious or a critical issue for the people involved. This is by no means a comprehensive list. In some cases, it is required by local codes and standards to have backup or emergency power. Engine generator sets are rated according to the application they are used in. Most diesel engine-driven generator sets are rated for standby power. A prime power application is basically the same engine generator set, which is used for a more than backup power generator. It can be run for more hours per year at a lower power level and still be an acceptable life expectancy. Generator sets used in utility programs to periodically reduce the load on the grid are rated for prime power. A generator set used for backup emergency power must be rated for prime power if it's used for a utility power curtailment program. A continuous duty rated generator set is suitable for running 24 hours, 7 days a week, and is shut down only for maintenance. These generator sets are used in applications where no utility power is available, or where the generator set is expected to base load on the utility grid to add power to the grid over long periods of time. Offshore drilling rigs for oil and gas, mining applications, remote resorts, or a cabin are some examples. In this slide, we have one example of multiple generator sets running in parallel with the utility grid to make up for power that cannot be generated by the local hydropower plant. The area is in a drought, and the water level is approaching a critical point where the hydropower cannot meet the demand for electricity. Many diesel generator sets are used in conjunction with utility power. The diesel engine short response time to changes in load offers advantages over turbines and alternative power forms of electricity generation. Most diesel engine-driven generator sets are used for standby power or standby power with occasional utility curtailment plants. I will now show some examples of standby power. Many of these applications are rated prime power, so the owners can use the generator sets for more than just standby. This can generate revenue or lower electrical costs for the facility. It is an exercise in engineering economics to decide when a diesel engine generator set may be used for a dual purpose. The higher installation cost and higher maintenance cost has to be weighed against the benefit of the revenue generated from the utility program. This is different for every installation. In this application, everyone can understand the need for emergency power. We don't want to be on the operating table when the utility power fails. An important point to remember about a hospital or similar critical application is that in these cases, the emergency bus is divided into 3 separate loads. Life safety loads are applied to the emergency generator first. Typically, the emergency diesel generator set restores power to the life safety loads in 10 seconds or less from the time the utility power outage is encountered. The essential loads are put on a few seconds later. The third item is the other loads, and these are applied last. This allows the facility flexibility to apply multiple transfer switches to the emergency diesel engine generator set. It allows for multiple generator sets to operate each bus or multiple generator sets run in parallel on the emergency bus. There are many ways to accomplish each individual hospital's requirements. A reliable, affordable, and flexible solution is attainable. Many healthcare facilities have standby diesel engine generator sets to provide power when utility power fails. This is a life safety issue as well as a necessary convenience for some residents. You don't want your heart-lung machine or your climate control or the food service interrupted. In the telecommunications industry, it is important that the communications are not interrupted. When the power from the utility is out, the phones continue to operate from an uninterruptible power system, or a UPS. This is a battery backup that uses an electronic device to convert AC power to DC. When the utility is off, the batteries supply DC power. A generator set is then started to supply AC power to the UPS system for the duration of the power outage, and the communications go on uninterrupted. These UPS systems are expensive to install and maintain. The size is limited to the power requirements of the telephone switching center, and the diesel engine generator set is sized accordingly. The same is true for cell phone communications. A smaller UPS system is employed at each cell tower. These UPS systems, these UPS power supplies are backed up by engine-driven generator sets. At this point, I want to digress a bit and talk about reliability. The customer depends on the communications provider to maintain uninterrupted calls. The cell phone provider depends on a backup power system to be there when the utility power fails. The backup power system consists of a diesel engine-driven generator set and a transfer switch. The transfer switch is a device that tells the generator set when there is a power outage. It starts the generator set automatically and transfers the load to the generator set from the utility. This prevents the generator set from sending unwanted power to the utility lines while the repairman is trying to fix them. When the utility power is restored, the transfer switch removes power from the generator set and switches the load back to the utility and turns off the diesel engine generator set. Both of these components are designed by the respective manufacturers to stringent industry standards to obtain an acceptable level of reliability. The manufacturers must ensure these components for their respective systems meet the applicable standards. These transfer switch and engine generator sets then must be installed per the applicable codes and standards and inspected, tested, and approved by the authority having jurisdiction before being commissioned for operation. When the standby power system is installed brand new, it is as reliable as it can be. To maintain reliability, it must be maintained on the manufacturer's recommended schedule. In some cases, there are regulatory agencies that dictate regular inspection and testing schedules for the emergency generators. If they do not get regular inspections and maintenance, they will not remain reliable. Two main failures for emergency generator sets are starting batteries that are dead or the insufficient fuel supply in the tank. Both of these issues can be avoided with a weekly inspection of the emergency power system. Municipalities are big customers for emergency power systems with diesel engine-driven generator sets. Most of us like the water supply to be uninterrupted as well as the electric power. It is good to have the sewer system working as well. There is no engine generator set customer more upset than the city manager who has to explain to the homeowners why the sewage lift pumps did not operate. Guess what backs up into the basement drains and toilets of the homeowner? Reliable backup power at the lift station can avoid this unhappy experience. Here's an example of a diesel engine generator set installed at a municipal sewage lift station. Another important user of diesel engine generator sets is the financial institutions and data centers. Their computers and servers are backed up by UPS systems similar to the UPS system in the telecommunications industry. There is no interruption in the very important money transactions. This bank uses a relatively small diesel engine generator set to operate the computers and lights only. Only limited building management functions will have power on the emergency power system. One may only have to go without the air conditioners until the utility power is restored. What size generator set is installed is a business decision based on cost versus risk. The essential items will have power. Some large data centers can require multiple large diesel generator sets for the emergency power system. Power requirements are large to support the computer servers loads as well as the requirement for environmental controls, heating, ventilation, and air conditioning. An emergency power system is required for any office building with an elevator or electric power-driven fire pump. The diesel engine-driven generator set fits this application best due to their ability to quickly respond to transient conditions on the emergency bus from changing load conditions. Elevators, ventilation fans, air conditioning units, and chiller pumps are some examples of these cyclic loads. There are thousands of emergency diesel-powered generator sets in the high-rise office buildings in every major city. Many people have never seen one or even know they are there. The building manager must keep close watch on the maintenance of the diesel engine generator set to ensure it will operate as required when called upon to run. When the diesel engine generator set does not run and the utility power fails is when the equipment is missed. This insurance company office building has some of its own insurance in the form of a diesel engine generator set for standby power. All major hotels have diesel engine generator sets. These units are usually large enough to continue necessary hotel operations in the event of the loss of utility power service. What guest would want the elevator, restaurant, pool, or bar to shut down in the event of a power outage? Agriculture is another large user of diesel engine generator sets. Every confined environment facility for raising livestock, producing eggs and poultry, or dairy barns use backup power. This is necessary to meet insurance company requirements and to protect the animals from suffocation in the event of loss of utility power. When we run into some applications, special considerations are given to sizing the diesel engine generator sets. Industrial plants, stadium lighting, and radar at airports are examples of some special requirements. In conclusion, I would like to highlight the points necessary for a reliable diesel engine-driven generator set used for standby power. The generator sets are designed and built to comply with industry codes and standards. Use of components that are complying with the applicable standards are required. The generator set selected for the application must be sized properly for the application to ensure it will perform as required for the loads to be powered. The generator set must be installed properly to ensure it will cool, breathe, and expel the exhaust gas safely and to operate as designed and not interfere with other building systems or surrounding conditions. The fuel supply must be easily serviced and installed to operate reliably. A rigid maintenance and service program are essential to ensure reliability over time. Diesel engine generator sets will be around for a long time to come. The emissions regulations will affect the use of diesel engines for generator set application, particularly for prime power applications. The diesel engine is still the most economical method to operate on-site electric power.
Great. Mike, thanks so much for that overview. It really does help to have a good sense of just how wide the uses are for diesel generators across so many different industries. And it's amazing. I think you were right that, I've probably never seen even a smattering of how many diesel generators there actually are in major cities, because they're all on roofs and they're just out of the way intentionally, obviously, to the general public. So thanks for that great overview.
You're welcome.
With that, I'd like to introduce our next speaker, Chad Dozier. And Chad is a marketing application consultant for Caterpillar's Electric Power Division. Chad has worldwide marketing responsibilities for diesel generator set solutions from 600 to 6,000 kilowatts, along with associated packaging control systems. Chad attended Purdue University, where he received a bachelor's in electrical engineering. And since joining Caterpillar, he's held various positions within the electric power division, including application engineering, 3500 generator set engineering, an NPI project manager, and a lot of different integrated systems and control engineering. So with that, Chad, thanks so much for being here with us today to talk a little bit about some of the changes in diesel generator technology.
Dawn, thank you. So what I want to talk to you about today is take you on a journey of the progression of clean diesel technology, kind of where we've gone, or where we've been and where we're going. So really, the progression of clean diesel started in 1990 when Congress and President Bush signed the Clean Air Act Amendment. This Clean Air Act Amendment gave the United States EPA the ability to regulate exhaust emissions from new non-road engines, basically reducing ozone by controlling the NOx and hydrocarbon output, reducing acid rain by controlling NOx and the sulfur dioxide, and ultimately improving air quality. With each new tier, if you can look at the bottom graph, tier of regulations introduced, you can see the amount of allowable PM and NOx has been dramatically decreased. Notice the size difference between the Tier 1 gray box and where we're at today with the Tier 4 red and blue boxes at the bottom. But that's our non-road engines. The EPA stationary regulations, which are primarily the ones that impact diesel generator sets for installations, were introduced later than the non-road regulations. Really, they started in January 2007 with the NSPS, or New Source Performance Standards, and the effort to harmonize the stationary regulations affecting the generator set, the limits and the timing with the non-road regulations. What we've seen over the last couple years, starting in 2007 through 2010, is the smaller engines in the less than 3,000 brake horsepower and less than 10 liter per cylinder were required to meet the non-road tier limits for the specific model year and power output of that engine, which is for the smaller engines, the Tier 3, the larger engines, Tier 2 outputs. But for the engines with a total brake horsepower greater than 3,000 bhp but less than 10 liters per cylinder, could still meet the non-road Tier 1 limits. For the much larger engines greater than 10 liters per cylinder, those would meet the marine tier limits specified for their displacement and maximum engine power. As we're moving into 2010 and beyond, specifically you'll be seeing 2011 Tier 4 regs. The stationary generator sets are going to be in alignment with the non-road and marine regulations for non-emergency engines, but there will be emergency engines that remain to the pre-Tier 4 emissions levels. Let's take a look at just some basics of air quality. As I mentioned before, the EPA regulates, really looks at 4 emissions that are put out by diesel generator sets. The first one is carbon monoxide. The second one is hydrocarbons, which is basically the gaseous compounds and unburned fuel in the diesel exhaust emissions. Particulate matter, which is a mixture of solids and liquids, and the NOx, or oxides of nitrogen. From an EPA standpoint, they really put the emphasis on measuring and monitoring and reducing the NOx and PM output. Now, one of the things as a diesel engine manufacturer that we are aware of and we have to work with is that NOx and PM act as trade-offs during the combustion process. So things that we do to decrease the NOx production will actually increase the PM production and vice versa. We also find from an engine manufacturing standpoint that the hydrocarbons and carbon monoxide also increase proportionally to the NOx reduction. So what are some of the things that we as diesel engine manufacturers and generator set manufacturers are doing to reduce emissions? Well, really, emissions reduction technologies can be kind of divided into 2 broad categories. The first category is engine technologies. These are things that we are doing on the engine pre-exhaust to basically reduce the emissions. The first one is working with the combustion control, which consists of increasing fuel pressures to decrease the formation of PM, or the particulate matter. We also are introducing NOx reduction systems, which basically allow us to recirculate a portion of the cooled exhaust gas, which allows us to lower combustion temperatures and decrease NOx production. But in some cases, this is not sufficient enough to meet the federal regulations. So diesel engine manufacturers are introducing aftertreatment. 2 types of aftertreatment focusing on reducing PM and reducing NOx. From a PM standpoint, the technologies we use are diesel oxidation catalysts, which these, the diesel oxidation catalyst uses a precious metal to basically break down the exhaust emissions. It's effective at reducing the CO and hydrocarbon output and has some impact on lowering the PM. Now, to further lower the PM, we can use a diesel particulate filter, which gives us up to about 90% efficiency in reducing the PM, but we require a regeneration cycle and soot removal. So as the filters gather and collect PM, we will need to basically raise the exhaust temperature to convert that PM into a soot and eventually clean the filters. Now, from a NOx standpoint, we're looking at using selective catalytic reduction to provide a increase in the ability, and a decrease in the NOx emissions. This is through, again, the selective catalytic reduction, or an SCR. The SCR reduces NOx emissions through catalytic reactions, typically using a urea solution, also known as a diesel exhaust fluid, injected into the exhaust stream. This diesel exhaust fluid will break down and release ammonia, which reacts to the NOx in the exhaust stream across the SCR catalyst to basically produce nitrogen, water, and carbon dioxide. Another advantage of the SCR system is it can also provide some levels of sound attenuation. So what are kind of some of the manufacturers' roles for, again, the diesel engine and diesel genset manufacturers' roles in clean diesel emissions? Well, ultimately our goal is to provide a combination of engine technologies and aftertreatment to lower the diesel emissions. Our goal is to really minimize the impact on the customer. So it's taking a look at all of the technologies we've got available, both the engine technologies and the aftertreatment technologies, and developing the proper solution based on the engine output. The other thing to be aware of from an engine manufacturer standpoint is our goals are to meet the EPA regulated emissions levels. So the Tier 2, Tier 3, and upcoming Tier 4 levels. Just something for everyone to be aware of is local air boards and emission regulations may be more stringent than the EPA levels for manufacturers. You'll see this oftentimes in non-attainment areas and in California with some of the regulations put forth by the California Air Resources Board. These local emissions levels may require some additional emissions reduction equipment, which brings us into the realm of retrofit opportunities. So when do we typically see our generator sets retrofitted with additional aftertreatment above and beyond what we would provide as a manufactured source? Well, typically it's when the regulatory or the regulations at a local level drive those requirements. One thing just to note and to make everyone aware of is there are the upcoming RICE NESHAP regulations, which will be covered in a webinar this coming Thursday. But with the retrofit opportunities, there's really a combination of aftertreatment options available that can really be designed to match the generator set performance. But there are some things that you'll need to be aware of when looking at retrofits. The first one is the generator set emissions level. When looking at retrofits, you need to know not only the emissions level that you need to meet for the installation, but also what your current emissions are for the generator set. And again, this will allow a vendor to provide you a different mix of aftertreatment solutions to meet the emissions levels. And this mix of aftertreatment solutions are really suitable for use with almost any diesel genset out there that's been manufactured. But ultimately, they need to be specifically matched to the generator set performance. Again, that NOx to PM ratio and the exhaust temps are very critical in the design and specification of an aftertreatment system. Another thing to be aware of are some space or installation concerns. These will vary depending on the aftertreatment solutions, but what we found is space is typically not an issue. The aftertreatment solutions are capable of being installed in the existing exhaust piping. And finally, something to consider from a retrofit standpoint is the additional maintenance and inspections. When you add aftertreatment equipment to a diesel generator set, this is adding additional equipment that needs to be taken care of to maintain optimal performance. So typically from a aftertreatment standpoint, you'd be looking at quarterly inspections just to visually inspect equipment to ensure performance, ensure there's no leaks. There'll be annual service that'll vary based on your generator set operating hours. And but the advantage is this maintenance can typically be performed at the same time you're performing the generator set maintenance and inspections. So the ultimate impact from a maintenance standpoint can be minimized. So just to wrap up diesel engines today, there have been a lot of advances in diesel engine technologies over the last 10 years. We've seen emissions decrease from our unregulated Tier 4 engines by approximately 90% in the reduction of NOx and PM. The engine exhaust is much cleaner today than it has ever been from any time in the past. And when needed, there are many technologies available to further reduce the emissions output of a diesel engine. And just what to leave you with, there's a very bright future for clean diesel.
Okay, Chad. Thanks so much for that presentation. It's amazing to see, obviously, how much change there's been in reducing diesel emissions over the years, and to see now, as you know, and many of the folks on the phone know, we've seen gone to the Tier 4 equivalent technologies in the on-road sector, particularly in the trucking and heavy-duty on-road trucks and buses, getting to that absolute lowest level of the equivalent of Tier 4, and now just coming on very shortly here in the off-road sector as well in diesel generators. So it really is a progression that's happening across, obviously, all diesel uses, and thus affecting so many industries, as we heard from Mike's presentation. So thanks so much, Chad, for that. Just a couple of things I want to mention before I introduce our final speaker, Mark. I do want to note that today's webinar is being recorded, and you can listen to the entire webinar or even just download the presentations from the DTF website at the conclusion of this webinar in about 24 to 48 hours after it concludes. So don't feel like you have to take copious notes necessarily during the presentations. You can actually download the full presentation after the fact. I also want to encourage folks, if you have questions during these presentations, things come to mind, please go ahead and you can submit them in the Q&A box that is on your screen. And when we conclude with Mark's presentation, we'll go back and address some of those questions. So please go ahead and feel free to submit them now. You don't have to wait until the end of our presentations. And with that, let me introduce our final speaker, who will be Mark Foreman. Mark is a Senior Product Manager for Hardware at Enernoc, and he's been at Enernoc since 2005, where he's been responsible for building a company-wide field organization and developing a team focused on process improvement and strategic planning throughout the entire company. He currently oversees Enernocs initiatives to find and integrate hardware solutions that best serve its key product lines. Prior to joining Enernoc, Mark served as an engineering and business consultant to federal, state, and local governments, public power agencies, and private clients, advising them on energy, finance, engineering, and environmental matters. He holds a BS degree in engineering from Lafayette College, a Master of Science in Engineering from the State University of New York at Buffalo, and an MBA from the Carroll Graduate School of Management at Boston College. And he's also a certified energy manager and a certified sustainable development professional. So, Mark, thanks so much for joining us today. And Mark is going to give a brief introduction to Enernoc, but talk about demand management and the role of diesel generators in that area. So, thank you, Mark.
Thank you, Dawn. And I'd like to thank Mike and Chad as well for excellent presentations and actually presentations that are a great lead-in to my discussion on distributed generation and demand response. What I'd like to talk about today is what is demand response and how does it work? Why participate in demand response? Where can I participate in demand response? And I'd like to end with a discussion on some key factors to consider when deciding how you enable your demand response participation. So the first question, what is demand response? Demand response, end users reduce their demand for electricity from the grid. What does that mean? That means the grid is calling on an end user, any of those end users that Mike showed you earlier, hospitals, data centers, office buildings. Every single example Mike gave earlier is a potential demand response customer that could reduce their demand for electricity and be paid capacity and energy payments much like a generation source. It's important to differentiate demand response from peak shaving. Demand response is not peak shaving. Peak shaving is a customer deciding on their own to operate their backup generation to reduce their load. Demand response calls are made by the grid operator in response to particular grid conditions. And this slide shows pretty well what sort of conditions utilize demand response. So as many of you know, in most utility systems, during less than 1% of the year do you need the last 10% of your infrastructure. So the graph I'm showing here, entitled entitled percent of system peak demand, is a snapshot of peak demand at a typical utility across a typical year. As you can see, there are very few hours where you need that last 10% of infrastructure. Further, as most of you know, utilities are required to keep a certain amount of additional generation in reserve in case of an outage. Often it's a function of the size of the largest generating unit or the two largest generating units. They're required to purchase capacity, have it ready to go in case there's an outage. Demand response allows you to have end users satisfy those reserve requirements and satisfy those peaks instead of traditional generation. So how does demand response do it? Demand response leverages existing infrastructure. It's all about reducing your load at your meter, and there's two ways to do that. You can curtail load, and that runs the gamut. If for those of you sitting in your offices right now, you can look up and see your lighting. You can look at those HVAC vents. Probably a lot of you right now have a lot of hot air being pumped into your office buildings. You wouldn't want to turn down your heat or turn up your air conditioning all year, but you could possibly do it a few hours a year and still maintain a comfortable environment. In addition, you could reduce some lighting, especially on a very bright day when you've got exterior light coming in. So if it uses energy, it can be reduced. The other way of enabling demand response is through backup generation. So using that backup generation, either controlled remotely by a grid operator or a third party like Enernoc, or controlled manually by on-site staff. Most self-generation for demand response is islanded using an open transfer switch. I'll talk about it in a minute. Some facilities do interconnect, and they do that for the reason Mike mentioned earlier regarding UPSs, where a facility can't have an interruption a brief interruption in their power. Sometimes they will operate interconnected to the grid, but by and large, a facility will shut itself off from the grid and operate independently. This slide is a great demonstration of how curtailment and backup generation can work together to facilitate demand response. This is a very typical grocery store demand response curtailment demonstration. So you can see that an RTO, which is a regional transmission operator, such as ICE in New England or PJM, calls an event. This particular facility responds automatically with 3 different types of response. It runs the small backup generator in the back of the facility that powers the front-end registers and servers. You raise air conditioning set points a few degrees, and you also reduce the lighting. That combined response reduces load at this facility by about 15%. It's all done remotely, and at the end of the event, the load is restored automatically. So demand response protects the grid and the public. It's very important to note that record peak demand isn't always what drives a demand response event. utilities procure enough power, they have enough infrastructure to satisfy their peak demand, even in a worst case scenario, in a situation where a long extended heat wave or a long extended cold snap. It's generally grid abnormalities that drive demand response event calls. A generator goes down unexpectedly. A transmission line goes down unexpectedly. And it's important to note that demand response enablement and demand response participation does help save the grid, which actually helps reduce the need for all backup generators. So all backup generators to run, that is, during a particular time. Because if the grid fails, all of these generators are coming on. Demand response allows a few generators to come on and help satisfy load requirements. DR programs rely on properly permitted generation. Before a site can participate in demand response, you have to make sure its permits are up to date for the particular jurisdiction and the particular type of use. Grid failures do have major impacts on public safety. During the August 2003 blackout, New York City's sewage systems failed. They weren't able to keep up without power, and one example of an environmental issue was many millions of gallons of untreated sewage being dumped. Lastly, a demand response event allows you to be aware of grid issues before they affect you. So a lot of the facilities that Mike showed, data centers, hospitals, and the like, require not just power, but require high-quality power. A demand response event can be an indicator of a power issue coming up. So why participate in demand response? Demand response works. So the graph here is an illustration of ISO New England's load curves on August 2nd, 2006. We have more recent examples in this, but this is a great illustration of demand response at work. The red line that you see on this graph shows what ISO New England anticipated their load to be had demand response not been activated. The orange line shows what their load actually was with demand response activated. So you can see this is all of New England, and you're seeing a nearly 500 megawatt reduction in the system peak because of demand response. Demand response is efficient. As you saw earlier in this presentation, demand response is addressing reserves, and it's addressing those peak few hours. Independent studies have shown that demand response actually can result in more efficient unit commitment because you're not trying to use base load units or larger units to satisfy very limited peaks. Demand response leverages your existing generators and gear. You've got this infrastructure already. It's at your facility. Chad gave some great examples of some of the newer equipment out there that's much more efficient, it's much cleaner. You've spent good money on that infrastructure. This is an opportunity to have that infrastructure work for you. And demand response complements maintenance and testing. Demand response providers are paid for performance. Ultimately, you get you're paid for what you deliver. So you want to ensure that those engines are kept in good working order. Mike mentioned earlier that a good maintenance and testing program is essential for emergency backup generation. Well, demand response participation provides further motivation to a customer to keep their units up and to help be reimbursed for the cost of the fuel, the maintenance, and upgrades to that equipment. So where can I participate in demand response? There are open market programs where you can participate, and there are different demand response aggregators, including ENERNOC, have programs with particular individual investor-owned utilities or IOUs. So an RTO, regional transmission operator, IOU, investor-owned utility. So the largest restructured markets that ENERNOC participates in, actually we participate in all of them, includes New England, New York, PJM, which is the Mid-Atlantic states out to Chicago, the Electric Reliability Council of Texas, or ERCOT, California, Ontario, Canada, and National Grid in the UK. Those are all open market programs where the regional transmission operator actually operates a program for demand response. Different demand response aggregators, including ENERNOC, also have bilateral contracts for demand response with particular utilities, and I've illustrated some of ENERNOC's bilateral contracts on this slide. So demand response in restructured markets, different markets use demand response for different purposes. All of them use it for capacity, to provide the capacity that fulfills that peak requirement and can fulfill that reserve. Some utilities are looking to use it just for energy only, so what's called non-firm commitments. And some of them are also piloting the use of demand response for what's called ancillary services, which is voltage regulation, frequency regulation, and a more distribution level regulation. Just getting into that further, an illustration of different demand response opportunities in PJM, so in the mid-Atlantic states. The largest program is the Emergency Load Response Program, or the ELRP. Excuse me, curtailment can participate in demand response. Generation can permitted generation can participate in many states, not all of them in PJM, but many of the states do allow permitted generation. Another type of program is an economic load response program where a customer can participate in response to price signals. That can require more rigorous permitting, but is also allowed in some states. The last is the synchronized reserve market, which goes to the ancillary services market that I talked about. That is also a program that requires more rigorous metering, more rigorous environmental permitting, but is a use for demand response for actually for localized grid control. So demand response in regulated markets. When ENERNOC signs a bilateral agreement with a particular utility, we're guaranteeing capacity, just like a power purchase agreement. We make a contractual commitment. We provide a financial guarantee to that, just as if we were a generating unit. Those programs are developed to meet utility needs and particular regulatory requirements, and we are contractually bound to deliver. So I'd like to end this presentation talking about 4 different factors related to particular customers' demand response participation. The first is remote versus manual control. Demand response can be initiated automatically or manually. So the picture on the top is our Network Operations Center here in Boston. And from this center, we can actually dispatch a customer's backup generator for a demand response event if they would like us to do so. If they would like us to set it up to be done that way, we can dispatch them. That makes it easier on the facility to participate. Somebody doesn't have to run around and turn on the generator, and can result in greater reliability. However, many facilities do wish to retain manual control, and in those cases, facility personnel will receive a phone call, an instant message, email, or a page to respond to a demand response event. They will, and in that case, they will turn on backup generation or affect their curtailment plan. This does make it easier on the customer to participate. It's an easier installation, but it does require the customer to be ready when a demand response event is called. Islanding versus interconnecting. So I mentioned most customers island. They have an open transition transfer switch where they will take their load and completely disconnect from the grid. This is an easier installation. It's a less expensive installation, and since most customers already do have do have open transition transfer switches, it makes it for a faster deployment. The challenge with that is that the customer will see the blip when transitioning from the utility power to on-site power. They will you're limited to the load connected to the generator, and most generators do have a relatively low % load versus what their capacity of their generator. Facilities can also interconnect either briefly or for a longer duration. That means the generator is connected to the grid directly. That provides a seamless transition. It allows the full capacity of the generator to be used. It does cost more to have a closed transition switch installed, and part of that cost is permitting, because oftentimes a facility that participates is interconnected requires a more rigorous air permit than a facility that is just islanded. We do find the vast majority of customers do island. Very few customers are grid synchronized. Air permitting and control. Chad gave a nice introduction and a nice discussion of some of the aspects of air permitting out there right now. It's important to note that reliability-based demand response programs, so programs that are called right before lights out, what is particularly called NERC, or National Electric Reliability Council Alert 2, are programs that are NERC Alert 2 programs are often considered under lights out air permitting regulations, which means when a reliability-based demand response event is called, it's much the same as if the lights were going out and they're permitted as the lights were going out. Some states treat reliability-based demand response programs like that. Some do not and require permitting similar to a peak shaving facility. Chad talked a bit about EPA tier readings, and it is important to note that local jurisdictions can set more stringent requirements than the EPA. Last is to note metering and monitoring. One of key aspects of demand response participation is that a customer is able to monitor their participation during a demand response event, and an aggregator such as Enernoc is able to pull that monitoring data in and examine how our customer is doing during a DR event. You can either monitor facilities right at the generator and watch their output, or you can watch load reduction from the meter. Why this monitoring and how is it important? Let me show you an example of a customer that actually had two different transfer switches. Hit one initially. Realized after a few minutes, we realized that they hadn't hit their transfer switch. Hit their second one, and they were able to show full performance. And that's all I have. Again, I appreciate the opportunity to present to this forum, and I will hand this back to Dawn and Kristen.
Great, Mark. Thanks so much for that great overview and getting us up to speed a little bit more on demand response programs and the differences between demand response and peak shaving. I think that was all helpful. So we've come to the end of our presentations now, and we have had some questions submitted, and so we will go through some of these. And as we're continuing on, if you think of other questions, please feel free to continue to submit them. One question, we had a couple of different people ask about the use of renewable fuels and biodiesel in diesel generators, and I'm wondering, this might go to, it could go to any of you. I mean, maybe I'd start, if all three of you could comment, and both in terms of, whether that affects, from Chad's perspective, in terms of the use of particularly the newer technologies and the retrofits, and Mike from a perspective of in different applications. I mean, what do you see around the issue of renewable fuels and biodiesel?
Well, I guess I'll start with that one. The biggest thing that you'll run into as you move into some of your your newer tiered engines with specifically biodiesel is just to ensure that you maintain kind of the same standard of quality that the diesel fuel needs. One of the things with the Tier 4 regulations is we are moving to a ultra-low sulfur fuel. And so when you are, if you're going to consider using biodiesel, you need to ensure that that biodiesel is mixed with again, the ultra-low sulfur fuel. And then mixes, obviously refer to your engine manufacturers, but typically we see B20 for most of the Tier 4 product is not a concern.
Okay. Mike, do you notice any different feelings on the use of renewable fuels and biodiesel depending on the application?
I would just add a couple comments to what's gone on so far with the biodiesel.
Mm-hmm.
This is the point that engine generator sets are rated and based on DF2 fuel. That includes their horsepower output, their performance, their emissions, everything that the published data indicates about the performance of the engine generator sets is based on a specific fuel type. One thing we've seen with the biodiesel around the country is that different producers of biofuel have different specifications and different outcomes of the biofuel, so it's not always consistent. So to predict the performance of the engine generator set, when the fuel changes, it's going to give you some variables. So your performance of the diesel generator set may change. Another thing is that when biodiesel is stored, it tends to break down much quicker than regular diesel fuel. And when it breaks down, it can cause problems with the filters, injectors, and other equipment on the engine generator sets. That doesn't necessarily make biodiesel bad for generator sets. It means that you've got to be careful of the applications you use it in. You need to turn the fuel over regularly so that you can get the best performance from the biodiesel.
Mark, anything you wanted to add relative to the application of demand response? Or?
No, other than to go back and ask Mike and Chad a question regarding additives, because I know that when we see backup generation, a lot of times the fuel has sat for a while because it doesn't get run regularly. Are there particular additives or other things you can do to increase the life of that fuel?
You want to go first, Chad?
Yeah, I was going to say additives are still available to be used. I mean, you can still use additives. You do need to be aware, though, that, again, make sure that the additives you're using are not going to raise the sulfur content of your fuel above the 15 parts per million for the ultra-low sulfur diesel. And also a lot of manufacturers will have a limit on the amount of additives you can use, such as like a 1-2% additive maximum that you can add to the diesel fuel.
I agree. The other thing you need to do is make sure the additives are approved by the engine manufacturer so you don't get any chemical reactions with seals or components inside the engine or the ancillary equipment that could cause you problems. The other thing I wanted to say, I just forgot, completely slipped my mind. Oh, and the other thing you can do with stored diesel fuel, if you have like DF2 fuel and it's on site for a long time, or there are systems out there like clean fuel systems where people who do clean fuel, where they pump the fuel out of the tank, run it through filters, or put additives back into it to recondition the fuel, and you don't have to throw it away. We do this for some of our places where they have very large fuel storage tanks and low usage, particularly on some government installations.
Okay, thanks. Another question we had, and maybe we'll start with Chad, and then if others have comments. The question was, why are the PM NOx ratio and temperatures important when considering further emission reduction technologies for generators?
Well, the key thing to know is, basically how is your current engine performing to know what the right mix of solutions are. Exhaust temps, we'll start with that one. They're important because you need to maintain a certain level or a certain temperature, certain minimum exhaust temperature to allow the chemical reactions that occur to occur. And then with the PM to NOx ratio, that goes to, basically the mix of technologies. If you've got an engine that has a low NOx, high PM output, you'll be looking more at maybe a diesel particulate filter, diesel oxidation catalyst combination. Or if it's a lower PM, you'll be looking more at an SCR system, or possibly, again, a hybrid of maybe all three technologies.
Mike, anything you wanted to add? Or? No. Okay. Mark, I have one for you here, and others as well if you want to chime in afterwards. The question was, how do you see the new definitions for emergency-only engines in the New Source Performance Review and NESHAP affecting demand response opportunities?
So there's two answers to that question. For non-emergency engines, or for engines that are treated, as I mentioned in one of my last slides, that some engines are treated as reliability, or treated as being in reliability-based programs or true emergency programs, and some programs are not considered that by regulators. For the programs that are not considered as emergency programs, those engines will require diesel oxidation catalysts after 2013. We do believe that in most cases that's a cost-effective upgrade for a customer. You get a cleaner engine, and the customer can still participate in demand response. For emergency programs, we and other demand response providers are working with the EPA on the particular hours limits in the NESHAP's regulation that would not require those engines to have upgrades. So we are working with the EPA on that issue right now.
Okay, and I would just add to that, to the person who submitted that question and others on the call, as we mentioned earlier, that we are having a second webinar on Thursday, kind of a follow-on to this webinar, and that will talk about in there we will have someone from EPA who will be talking specifically about the NESHAP for rice rule, and so you can learn even more about that if you're able to participate in that one. And
yeah,
like the case with this one, if you're not able to participate, that will also be recorded and available afterwards if you can't participate yourself at that time. Another question that came in again from Mark was asking if you can elaborate on the islanding scenario of demand response capacity differences. For example, I'm just going to read this here. Will we only get 30% of the rated power from a generator that's islanded as opposed to connecting in parallel?
So the 30% is, let me talk about the number and then talk about the concept in general. So the 30% is a rough average of what we see. What's happening in an islanding situation is that what you get is whatever load the customer has put on that backup generator. So when the generator was installed, the customer wires certain of the electrical panels into the emergency power system for that facility. So whatever's on that emergency power is what the generator will carry. And our experience shows that customers often don't put all of the systems in their building on their emergency power system. So often an office building, for example, might not anticipate the building to be occupied for many hours on their backup generator. They might have it, to be able to stay in the building for a couple hours, but realize that if the power stays off for a long period of time, ultimately the temperatures will rise too much and people will have to leave. So because of that, they often underload their generators. Hospitals and data centers generally don't do that. Obviously, and elaborating on what Mike talked about, a hospital is going to put their critical systems on there. You can't just, if the power goes out for 2 hours, you can't just have everybody leave. So when you're islanding, you're capturing whatever load was wired into that generator, and just our experience shows that the what's wired in versus what the generator could take is a relatively low percentage.
Okay. Another question was with regards, and maybe Chad can start, but for any of you, several of you mentioned about the fact that there can be local regulations restricting emissions from diesel generators that are more stringent. And I'm wondering if you could talk just generally about that. I mean, are there many local regulatory authorities that do have, their own separate, stricter regulations, or not, or just kind of characterizing that?
Sure, I can
Chad,
start with that.
Do you want to start with that? Okay.
Yeah, I'll start with that. Basically, every state has its own local air regulatory board, and states are divided up into even local territories within the state. And it's really critical, as a customer and end user of the equipment, to know the specific area you're in and the specific regulations that apply to your generator set. Like I said, there's a number of websites out there that can help direct you to your correct air boards. Again, like I said, each of those air boards are responsible for maintaining the air quality kind of in their regions. I guess, Mark, you can probably add to that.
Sure. So, just as Chad said, so you've got the EPA, and below the EPA you have the 50 states. And with some states it stops at the state level, but in other states there are regions. Also, you can have counties, and even down to the point where some cities actually have their own regulatory board. And so, in different regions, different areas, the governing regulatory body can be different. And as Chad said, it's essential when you're putting in a backup generator that you work with the regulating air board. And Chad mentioned the web's the great resource. Consulting engineer would be a great resource as well. I can tell you here at Internoc we have a staff devoted to air permitting, and that staff spends 100% of its time working on permitting, relationship building, working on regulations with applicable air boards. So, people operate backup generators continuously, obviously, or install them and have them available all the time, and they're always installing new ones. But you really want to make sure that you're working with that governing regulatory agency to make sure that you are in compliance.
And then just a follow-on to that, are there when these local bodies are have their own regulation, are they likely to make it across the board for all applications of diesel generators, or are they frequently different based on the application of the generator?
It can actually depend on it depends on the regulatory board and the particular interest that they're addressing, and the particular concern that they're addressing.
Mm-hmm. Okay. And then just one other question I have here from Mark. In terms of peak shaving versus the demand response, and you had talked about that definition earlier on. Based on the definition you had given, it sounded like peak shaving was more the case when the user or the owner of a diesel gen set instituted coming off the grid him or herself, as opposed to a demand response where the grid reliability is at risk, and the utility is calling for folks to get off the grid to reduce the load. I'm wondering if you can, number one, confirm whether that's true, and then, and if not, explain why not, and then explain a little bit about why would the user want to get off the grid and use their own, backup generators if there's not an emergency and a need to do that from a reliability standpoint.
Okay. Part one is, yes, that definition is accurate. So in a nutshell, demand response is a grid call for load reduction. Some facilities do shave their peaks, and they can do this with with renewables. They can do it with properly permitted diesel backup generation. But the reason they would do that would be to reduce their peak demand or reduce their demand charges. So if you get into a larger facility, they may only be able to purchase a certain amount of capacity. They may have physical restrictions. They may just choose to not purchase power from their utility above a certain power level. So the decision to peak shave is an individual customer-driven one, usually driven by either driven by economics or driven by grid reliability issues. So then that becomes an individual customer by customer issue. But if a customer is peak shaving, that is a much more rigorous permitting process than a demand response by and large, and that is something where you absolutely positively need to be working with your local air board, and possibly an external consultant on if you're considering such an application.
Mm-hmm. Okay, I think we've gone through most of the questions that we've received from our attendees. Let me just ask if any of our speakers had any last comments or thoughts that came to mind that you wanted to share. And if not, that's fine, but I just wanted to ask. Okay, well, hearing none then, I want to thank our speakers and certainly all of our audience members for your participation in today's webinar. We've mentioned a couple times, just a reminder to all of you that our second webinar, which is going to focus on technology, trends, and regulations, we'll get into some more of these regulation issues in that second webinar, which will be held at 2 p.m. Eastern Standard Time this Thursday. And again, if you're not registered but you're interested in registering, please visit www.dieselforum.org/webinars, where you can still sign up. Speakers on that webinar will include a representative from EPA discussing the agency's niche app for ice regulation that we talked about. There will also be a representative from the Delaware Division of Air Quality discussing the Ozone Transport Commission's recently adopted model diesel generator rule. And then also a representative of Cummins Power Generation looking at the differences between diesel and natural gas-powered generation and the factors which define the growth opportunities for diesel generators. And finally, again, if you'd like copies of today's presentations or have colleagues who are interested in today's session but who are unable to participate, please remember that you can download the presentations or listen to an entire recording of today's session, which will be posted on the DTF website in the next 24 to 48 hours. So with that, I want to thank you very much for your time and attention, and I want to wish everyone a warm and safe and happy holiday season. Thank you. This concludes our presentation for today.